Okay, let's just start with a scenario. I mean, it's a bit of a worst case one, but imagine this. You or maybe someone you know has swallowed something sharp.
A truly terrifying thought.
Absolutely. And the immediate danger, it's not just that the object is inside you. The real life-threatening risk is getting it back out. We're talking about trying to pull, say, an open safety pin or a razor blade back up through the esophagus without causing catastrophic
Without
damage.
lacerating everything on the way out, yeah.
And that very problem, that challenge of safe extraction, is what we are deep diving into today. And I want to be really clear about our source. Our insights are coming directly from a video transcript from the YouTube channel of Dr. G.S. Raju.
A fantastic resource.
It is. The video is titled HCC 1472 Lesson 12 Foreign Body Retrieval Hood. So our mission today is to really unpack this incredibly clever yet surprisingly simple tool called the endoscopy hood. We want to understand how this little rubber accessory makes a dangerous procedure safe.
And it really is a cornerstone technique. Foreign body retrieval or FBR, it's a common procedure. But like you said, when the object is sharp, the whole game changes.
The stakes are just infinitely higher.
They are. The problem isn't getting to the object. We've got endoscopes for that. The problem is protection. If you're dealing with an open safety pin, that exposed point, or the edge of a razor blade, any wrong move on the way up can be devastating. This hood technique is just essential.
So let's start with the tool itself. The source describes it as a very flexible, rubber-based hood. That sounds almost too simple for something so critical.
It does, doesn't it? But its simplicity is its strength. It's specifically designed to be attached right under the tip of an endoscope.
And that flexibility, that rubber material, is that the key?
That is absolutely the key. The material science here is critical. If this hood were made of, say, a rigid plastic, it would just be useless. It would probably crack or bind under pressure.
It wouldn't be able to perform the main action.
Exactly. The rubber gives it the pliability it needs to do its job, which is essentially this crucial flip we'll get into. It's also smooth enough for insertion when lubricated, but has enough friction to grip when it needs to. It's really a dual-purpose design.
That makes sense, because you're not just dealing with one type of sharp object. You have things like razor blades, which are flat, and open safety pins, which have a completely different, three-dimensional threat.
Precisely. The hood has to be a universal solution. It needs to create a safe little envelope around whatever the physician manages to grab, making sure no sharp edges are exposed to the esophageal wall.
Okay, let's unpack the setup process then. I think understanding the why behind each step is important here. So first, the hood is attached to the endoscope. Simple enough.
Right.
But then the physician has to flip the hood backward. Why backward? Why not just have it facing forward, ready to go?
That is a fantastic question. And it's all about navigation. Think about it. If the hood were deployed forward, it's wider. It would create a lot of friction and resistance going down through the throat, the hypopharynx, and into the esophagus.
It would be like trying to push a parachute down.
A small one, but yes. By flipping it backward, you streamline the whole tip of the endoscope. It creates this smooth, rounded leading edge that can just glide down to the stomach with minimal trauma. It's all about making the journey down easy so the journey up can be safe.
And the source also really stresses generous lubrication. I guess that plays into the same idea of a smooth entry.
It does, and it's more important than it sounds. If the rubber snags on any tissue on the way down, it could flip forward too early or get dislodged, and then the whole procedure is a bust before you've even reached the target.
You'd have to pull it all out and start over.
Exactly. Increasing time, increasing risk. So the lubrication ensures the whole setup stays intact all the way down to the stomach where the object is waiting.
So the endoscope is in the stomach. You found the object. Let's stick with the open safety pin. How do you actually grab it? It must be like one of those claw machine games, but with incredibly high stakes.
A very, very precise claw machine game, yes. The physician uses something called foreign body grasping forceps. They're these long, thin instruments that are fed through a channel inside the endoscope itself.
And you can control them from the outside.
Right. You need immense precision to get a secure grip on a slick piece of metal. If you don't get a good purchase on it, you risk dropping it, and like we said, you're back to square one.
Okay, so the pin is secured. The endoscope is ready. Now comes the dangerous part. The journey back out. This is where the magic of the hood comes in. This isn't just a straight pull, is it?
No, not at all. This is where the design leverages the patient's own body. The most dangerous part of the trip back up is passing through the narrowest points, particularly the lower esophageal sphincter. the LES.
The LES. Wait, isn't that just the muscular valve that keeps stomach acid from coming back up?
That's the one. It's normally a barrier, a one-way gate. But in this procedure, its role as a barrier is exactly what we need. It's turned into a safety trigger.
That is fascinating. So you're using the body's own structure to activate the tool.
That's the genius of it. As the doctor starts to pull the endoscope and the safety pin back up, that backward-flipped rubber hood runs right into the tight muscular ring of the LES. The source says it will catch on to the lower esophageal sphincter.
And here's where it gets really interesting. So the doctor's pulling up, the LES is providing resistance.
Yeah.
What happens?
That combination of forces, the upward pull from the doctor and the downward resistance from the LES, forces the flexible rubber hood to invert. It flips forward, right over the safety pin.
Wow. So that's the aha moment. The anatomical choke point, the place where the risk of tearing is highest, is the very thing that triggers the shield to deploy.
Precisely. It snaps into place at the exact moment you need it most. It's a passive deployment system.
Which is so much better than a manual one. You take human error, timing, and pressure out of the equation.
You absolutely do. If the doctor had to press a button at the exact right millisecond while navigating through the LES, the margin for error would be huge. This design makes the deployment automatic and foolproof. The body's own architecture guarantees the shield deploys perfectly every single time.
So the result is, the sharp point of the pin is now completely covered by this rubber hood. It's basically a protective sleeve.
It's a non-lacerating sleeve.
Mm-hmm.
As the object is pulled the rest of the way through the esophagus and out of the mouth, its sharp edges never make contact with the tissue. It's an incredible improvement in safety.
It's such an elegant solution. It shows you that medical innovation isn't always about lasers and robots. Sometimes it's about a clever piece of rubber and a deep understanding of simple mechanics and anatomy.
It really is. It reinforces that some of the best solutions are simple mechanical principles that work with the body, not against it. You're using a passive system, leveraging an existing anatomical constraint to solve a life-threatening problem.
Which leads to a really interesting thought, something for you to consider. We think of the LES as just a valve, right? A barrier to prevent reflux.
That's its primary job, yes.
But in this deep dive, we've seen it repurposed into a mechanical safety trigger. And that makes you wonder, what other parts of our anatomy, these structures we see as just barriers or pathways, could be leveraged in other unexpected ways to make medical procedures safer or more effective?
That's a great question. It challenges us to look at our own anatomy not just as a map of parts, but as a potential toolkit full of untapped mechanisms.
A toolkit. I love that. A truly thought-provoking way to end. Thank you for joining us on this deep dive into the brilliant mechanics of foreign body retrieval. Keep exploring those ingenious solutions.